doesn't prove that it isn't sufficient. You can have things that are both necessary and sufficient for other things. This is quite rare. But let's test our knowledge of necessary and sufficient. Okay. Is being unmarried necessary for being a bachelor? Yes. Why?
Or the definition of being a bachelor.
Yeah, you can't be a bachelor without being unmarried, so that's necessary. Is being unmarried sufficient for being a bachelor?
Are unmarried women counted as bachelors?
What's that?
Are unmarried women counted as bachelors?
No, they are not. So that proves
That it is not sufficient.
it's not sufficient. Yes, simply being unmarried doesn't prove you're a bachelor, because if you're an unmarried woman, you're not a bachelor. All right, what about, so being unmarried is necessary but not sufficient for being a bachelor. What about being an unmarried man? Is that sufficient for being a bachelor?
Yeah.
If it's not,
Oh.
if being an unmarried man is not sufficient for being a bachelor, then you should be able to come up with a counterexample. A counterexample would be an unmarried man who is not a bachelor. Can you do that?
A widower.
They're still bachelors, I think. We don't think of them as bachelors. Like, you know, your grandparents are both 99 and your grand dies. You don't think suddenly, grandpa's a swinging bachelor, right? But technically, I believe he is a bachelor. You can be both a bachelor and a widower. All right, so let's say being an unmarried man is sufficient for being a bachelor. Well, there's one of the rare examples where it is both sufficient and necessary, right? So being an unmarried man is sufficient to prove that you are a bachelor, and it is necessary for being a bachelor. You can't be a bachelor without being an unmarried man. So that kind of case happens when basically the two sides of the equation are identical. Right? Being you is both necessary and sufficient for being you. Right? If you are you, that guarantees that you are you, and you can't be you without being you. So when two things are identical, one is both necessary and sufficient for the other. But usually it's one or the other or neither. Let's see. Is being Pluto sufficient for being a planet? No. Is being Pluto necessary for being a planet in the solar system?
Definitely not.
Who says yes? Who says no? Why is it not necessary? Now I'm going to have to silence you again, Don. Why is it not necessary? No, that doesn't prove that it's not necessary. Why is being Pluto not necessary for being a planet in the solar system? Because there are other planets. There's, you know, there's 8 planets besides. And is being Pluto sufficient for being a planet in the solar system? No. And the answer is, well, at least not since the mid-aughts. Because poor old Pluto got demoted. Although I've heard recent rumblings that Pluto's place might come back. Why was Pluto demoted? Does anyone know?
It does not clean its neighborhood.
Is that right?
That's a phrase to say that it has other orbiting bodies in its path.
Oh, okay. I didn't know that was the reason. It also has a moon that affects it, so they sort of orbit around each other. But yes, it's basically too puny. And also, the other reason is, if we let Pluto in, we'd have to let all these others in too, because there's others about as big out in that region. And they don't want to, because they would go the neighborhood. But I've heard that maybe it'll get back in, which those of us who grew up with Pluto as a planet would be pleased. All right, so one more example. I believe I've done this example already. I'm sure I have because I like this example, but let's go over it again. Smoking, is that a sufficient condition for getting lung cancer? You're a smoker, you should hope not. No, it is not sufficient for getting lung cancer. What kind of person proves that smoking is not sufficient for getting lung cancer? No. What's that?
They smoke and they don't get lung cancer?
Yes, the lucky smoker, the smoker who does not get lung cancer. There are such people. My grandpa smoked a pipe from the age of 12. I think that's cute, a 12-year-old pipe smoker. A little scary, but it was cute back then. And until basically age 90, and then he gave up smoking and his health deteriorated rapidly. But he had to give up smoking his pipe because he kept falling asleep and then setting his blankets on fire. So it's not sufficient. Smoking is not sufficient for getting lung cancer, and the person that proves that it's not sufficient is the lucky bastard. All right. Is smoking necessary for getting lung cancer? No. Who proves that? Jordan?
Walter White.
Walter White. Right. Why?
Because he never smoked anything.
That's right, because if you've seen Breaking Bad, the main character, this is not a spoiler, he gets this in the pilot, gets terminal lung cancer and he never smoked a day in his life. He's a chemistry teacher. Chemistry teachers are insane. Did I tell you this about, I had a high school chemistry teacher, and he would do things like, he would show us a slow reaction, you know, a chemical reaction that took place slowly, and he said, okay, that was a slow one, I'm going to show you a fast one. All right, so you're going to have to all come in close because this is going to happen really fast. And he got this canister that was unlabeled and started filling up a plastic bag with whatever was in the canister. He said, come in close because this is going to be really fast. Then he got a lighted taper and he pushed it through the plastic bag into the bag, which was full of hydrogen. Boom. So consequently we were deaf for the rest of the class, and he thought this was hilarious because, you know, massive explosion and we all fall over. That's chemistry teachers for you. The other thing, he did other things like he had this glass jar full of powder, you know, he had tons of them, and he said, and he took it to this girl on the front row and he said, taste it. And she looked at him because she knew it was insane. And he said, no, it's perfectly harmless. So she tasted it and said, do you recognize the taste? And she said, no. And she says, good, because it's urea.
Oh, delightful.
Do you know what urea is? It's in urine. So there you go. He was nowadays he would be a lawsuit waiting to happen, but those were simpler times. All right. So you got the difference between necessary and sufficient. There will be questions on that on your homework. I think now we should start on a new chapter, chapter 12. We only have 3 chapters to cover for the final, and this is one of them, and we're going to cover this in very quick time. So chapters 13 and 14, you will probably gather, are going to be tough, which is why we're going to take them slow. I have learned through experience how to pace this course. Yeah, the stuff we're getting to now, it's different. Like I said, the midterm, we covered a lot of stuff, but it was all fairly simple stuff. Even, you know, Venn diagram stuff. There was only a few rules to learn. So we just learned a lot of stuff, and then, you know, the questions themselves are fairly simple. What we're coming to now is, well, the main part of, there are 2 main parts of what we're going to do. One is symbolizing, first in regular propositional logic, that's what we're going to learn today, and then later in predicate logic. So that's one main thing that we're going to be doing, and the other main thing that we're going to be doing is proofs. Now, proofs are fun, aren't they?
Oh yeah.
Yeah, proofs are fun, says Eric, who did well in the class. Some of the people who did not do so well in the class probably would not agree, but I think a lot of people discover that they really like proofs, even if they didn't necessarily like some of the stuff in the early part of the course, because proofs require more of you, but they're a bit more interesting. They're like little puzzles that you have to solve, and you have to learn kind of strategies for solving them. So that's why we're going to take a lot more time doing this stuff. It will be, some of you will find it very rewarding. Some of people come up to me years later and say, I really loved that logic class, those proofs, they were cool. So, you know, come to me later, I'll give you proofs to do in your spare time. But you will find that we need to practice that a lot. All right, so chapter 12. Now, chapter 12 is a little bit of a continuation of stuff that we learned just before the midterm. Because what we're going to start doing is symbolizing, and we've already done some of that. Everyone's got one of these? Right? Okay. Let's, well, we're going to do the exercises in a second. But before that, let me do a little table. Okay. So, before the midterm, we did some symbolizing. Here is an example of some of the symbolizing we did. Say, there's an example of this categorical syllogism in, you know, English words, although they're not complete sentences, and we symbolized it. We replaced each of the component propositions with a letter. We replaced each of the logical words with a logical symbol. And here's another example, and that's symbolizing. The good thing about symbolizing is it exposes the logical form of an argument. You no longer know what this is about. You don't know that this is about Ebola once I symbolize it. But you can tell pretty directly, you're not distracted by what it's about from what its logical form is. And once you've revealed its logical form, you can tell whether it's valid or not. So symbolizing is sort of like translating into a simpler but purer kind of language. And the language that reveals the logical form of an argument. So that's the point of it. And we need, to be able to do it, we need a sort of library of logical symbols. Some of them we already have. Okay, so I'm going to draw a little table to summarize this information. The first column I'm going to leave blank for now, and I'm going to call it herald words. This is my own terminology. You won't find this in the textbook. Herald words are a bit like indicator words. Well, they are indicator words, only they're not like therefore, which is an indicator word for a conclusion. They're indicator words for logical terms. All right, so I'm going to leave that blank for now, and I'll explain it in a little bit. But perhaps the most important...
Is this one that you want me to use?
Yes, this... Yes. But it's going to... some of it will already be familiar. Logical words. If I'm writing it down, it's gold dust. You should write it down in your own blood. So you never need to ask if it's important. All right. Logical words, symbol, the symbol for the logical words, and the name of the truth function. Now that sounds scary as well, but I'll explain that in a second. All right, so we've already come across some logical words, like not. What was the symbol for not?
Tilde?
Tilde. The tilde, that's right. Not the tilde or tilde, the tilde. The squiggle. Now, that is the symbol that we are going to be using. I will write in a different color an alternative symbol that you might come across elsewhere. I don't know why you would, but you might. There are other... This is not the only way of symbolizing tilde. It's the way that we will use in this class, but sometimes this is used. You might have seen that. Okay, now the name of the truth function is negation. Now, an exact parallel for this might be if I were doing this for, if I were making this table for arithmetic functions. If I was doing that, I might say something like the word would be plus. I would use an ink that you can actually see. Yeah, the word would be plus. The symbol would be the little cross, and the name of the function would be addition. Okay, but you learned that so long ago, that doesn't seem scary. Well, we're doing exactly the same kind of thing here, except where this is an arithmetic function, we're talking about truth functions. And actually, truth functions are a lot easier than arithmetic functions, because arithmetic functions deal with numbers. How many numbers are there?
No idea.
Well, there's a name for that. Infinity, yes. There is an infinite number of them. Whereas, how many truth values are there?
2.
2. 2 is a bit less than infinity, right? So that makes this a lot easier, as we'll see. All right, but that's essentially what we're doing here. Okay, let's get rid of, push that off the top. What other logical words have we come across? And. What symbol do you use for and?
Ampersand.
The ampersand. Now, be honest, who doesn't know how to draw an ampersand? Ooh, a lot of dishonesty.
You showed us, so.
I showed, I'm getting see now. Well, I'm going to show you again, because I love doing it so much. All right, so here is your space for your ampersand. You start in the bottom right-hand corner. You do a backwards slash and then a backwards S.
There will never come a day when I don't see that as a guy doing the dog with worms thing.
The what?
The thing a dog does when it has worms.
Well, I don't see that, so I'm not going to try and see that. All right, so that's an ampersand. Ampersand. Learn it, love it. Now, turns out that's actually not the most common way of symbolizing and. However, it is a very intuitive way because that's what we use for the word and. You see it in movie posters. However, another way that they actually use in the book, which I quite like, is this, the big fat dot. The reason why I don't want you to use this, and the explanation for the symbols that I use is they will never be confused for each other. Okay, that's the main reason for my selection of the symbols that I have you use, is that they will never be confused for each other or for anything else. The trouble with the dot is that people tend to get lazy and they tend to just do that, and then you can't see it, right? And you don't, and I don't know if you've actually put a dot there, particularly if you're writing in pencil and you're trying to be deliberately ambiguous so that you can get points when you don't deserve them. Not that you would do that. So I'm going to have you use the ampersand because that's pretty obvious. Another symbol, rather old-fashioned symbol for and, is this. You might have seen that before. The reason why we don't use that is because it's easy to confuse with another symbol that we're going to use, that we've already used. But what is the name for and? Conjunction. All right, another logical word. Or. What is the symbol for that? Little v, which of course is an upside down version of that, which makes it easy to confuse, which is why we don't use that for and. What do we call the function that is or? It's not conjunction, it's disjunction. It's when you are disrespected by a junction. All right. We have also used one more symbol. Then, that's right. The symbol, this is the symbol we used. And what is the word it replaces? It's not if. Because remember, if P, then Q, we symbolize as P arrow Q. So what word gets replaced by the arrow? It's the then, not the if. Okay, so then goes here. Now, this is not the symbol they use in the textbook. What is the symbol they use in the textbook?
Looks a little like a set
Yes,
symbol.
exactly. It's called the horseshoe. Looks like this. I always think of it as kind of like a Pac-Man going from right to left. But that's just me. That's my problems. But I don't like it. I don't like it, so we're not going to use it. It's ugly. I hate it. But you need to recognize what it is. I think the arrow is just much cleaner and it's much more intuitive. If P arrow Q reveals that P gives you Q, which is what it means. P is sufficient for Q. Now this is called the conditional, which is why hypothetical propositions are also known as conditional propositions. There is one more. And actually, it's a whole bunch of words that get replaced with this symbol. It's if and only if. Now, what that means is something we've just been talking about. If you say P if and only if Q, you mean P is both necessary and sufficient for Q. So you see that you would say being a bachelor is both necessary and sufficient for being an unmarried man. You could say you're a bachelor if and only if you're an unmarried man. Where does this come up? It comes up a lot in definitions, because what you're trying to do when you give a definition is you're trying to give a list of conditions for being the thing that you're defining that is both necessary, where each of the conditions is individually necessary, and put them all together, they're jointly sufficient. So for example, an example of this would be something that I happen to know from another textbook I've used, not because I've been found guilty of this. To be guilty of breaking and entering in North Carolina. Here is the definition. You are guilty of breaking and entering if and only if you broke into or just entered a building without the owner's permission. Why are those three? Each of those three is necessary. That is, you cannot be found guilty of breaking and entering unless you do all of those three. But why aren't those three sufficient?
If one of them isn't.
No, suppose you do all three. Why aren't you automatically guilty of breaking or entering? Who would that make guilty that we don't want to make guilty? So they broke into or entered a building. Incidentally, why do you need the building?
Otherwise, it's just trespassing.
Because it could be trespassing. If it's like breaking into a yard, it doesn't mean that you're innocent, it just means that you're not guilty of that particular one. Or if you break in and enter someone's car, that's not breaking and entering, that's something else, like vehicular something, theft. Okay, so you entered a building without the owner's permission. What?
Maybe if you
Could just
live in a
emergency
building.
responders.
Emergency responders, yeah. But you did that to get here. You came into this building without the owner's permission. Did you ask UM-Flint before you entered this building? I don't think so. But you're not guilty, so you need the fourth condition, which is with criminal intent, with intent to commit a felony. That, of course, is the hardest one to prove, but it is required, because otherwise firefighters would be perpetually guilty. So each of those conditions is necessary, taken together. If you meet all four, that is enough to guarantee that you are guilty of that. So so you come across this saying, if and only if, sometimes abbreviated as IFF. If in your spare time, as you do, you're reading philosophy articles, and you come across IFF, that's what that means. The symbol for it, here's actually a nice symbol that kind of goes with the symbol that we've already used, and it makes sense, but we're not going to use it, is a double-ended arrow. Because essentially it's meaning that, because the arrow means the first one is sufficient for the second one, but if it's necessary and sufficient, then the sufficient goes both ways. So P is sufficient for Q and Q is sufficient for P. So this would make great sense. The reason why we don't use it is it's easy to confuse for the single-ended arrow. So what we do use is this, which is basically three parallel lines, sort of a super-duper equals sign, which also means is logically equivalent to. And this is called the biconditional, because it goes both ways. It's not at all confused. All right. Herald words. Herald words are like indicator words. Remember thus and therefore and because and since. Those were all indicator words that revealed the logical form of something. When you wrote out the propositions, they went away. You didn't include them. They weren't actually part of the propositions. They were just something that told you some information about which one of them was a premise and which was a conclusion. Herald words are a bit the same. They disappear and are not symbolized at all. But it turns out that they are actually useful, we will discover, for the placement of something other than symbols and letters. What is that thing? You'll find out. I like a little mystery. Now, what is the herald word? Oh, incidentally, what is a herald?
Announces arrival.
Announces the arrival. That's exactly right. So, for example, if you're watching an old movie or Disney's Alice in Wonderland, not the Johnny Depp one, the animated one, and somebody runs in front of the king or queen with a little trumpet and goes, "Da, da, da." Here comes the king and or queen. That's a herald, right? It means an announcer. Someone who goes before and announces the arrival of. Okay, what is the word that goes before then and announces that it's coming?
If.
If. So if is the herald word for then. What is an optional word that goes before or often? Either. Yes, correctly pronounced too. Now you don't have to say it, but we'll find out that sometimes it's useful for revealing the position of something which I'm going to tell you about later. Not doesn't have one. If and only if doesn't have one. It's got enough words already. There's a word that you basically only ever use when you want to provide a herald word for and it is both. So for example, I can just say today is Monday and this is logic, or I can say both. Today is Monday and this is logic. They mean the same thing, but both tells you that the word and is coming. Okay. Now, that's actually a fairly small subset of truth functions. But it turns out you can do a lot with this small subset. It also turns out that each of these things, like addition or subtraction, does something. Performs a function, performs a truth function. Now remember, what a function is simply something that takes inputs and produces outputs. So addition is a function that takes two numbers as an input and produces a single output. Each of these is a truth function, which means that instead of their inputs and outputs being numbers, as in addition, the inputs and outputs are truth values, truths and falses. Okay, that's the basic idea. Let's do a little bit of symbolizing. So get out this sheet and let's look at the exercises. Everyone got one? Kat, start us off. Read the first sentence first, please.
Oranges contain vitamin C and baseball is played with a ground ball.
So what we're going to do is just like we did with these things, we're going to replace each of the component propositions. A component proposition is something that doesn't have any logical words in it. It makes a claim, it can be true or false, and you can't break it down any further into things that can be true or false. How many component propositions are there in that sentence? Two. The first one would be what? Orange juice contains vitamin C. Yes. And then the second one would be baseball is played with a round ball. And is won by the Royals. So, what we're going to do here is we're going to symbolize each of those with a letter. We don't have to use P's and Q's, that's boring. We can use words like, let's use O for orange juice contains vitamin C, although of course O doesn't just stand for orange juice, it stands for the whole thing because it has a truth value. And B for baseball. And then, so we have O and we have B. Now, here's an important fact. you never ever have two letters right next to each other. Something must come between them. What is the something that comes between them in this case? Cat.
I can't remember
Say it after me. Sand. Like I said, I've had people call that the Amsterdam before, so you wouldn't be alone in not knowing it. But it's ampersand. And it looks like this. What a beautiful ampersand. Look on it in wonder. All right. There we go. We've symbolized that sentence. Pretty dang easy. Right? And certainly the beginning ones of these will be easy. It'll get tougher. Now, having symbolized it, though, you'll notice that all of these examples are rather artificial. Why are we talking about orange juice and baseball? What's the point of this? Well, the reason why I picked these, and the reason why they're different from the ones in the book, is because I wanted to pick propositions that we knew the truth value of. What is the truth value of O? A little bit of general knowledge is required for this. What is its truth value? True or false? It's true, because in fact orange juice does contain vitamin C. It's part of a nutritious breakfast. All right, baseball played with a round ball. True or false?
True.
True. So notice, we know that the first conjunct is true, and the second conjunct is true. Knowing that allows us to work out the truth value of the whole thing. What is the truth value of the whole thing? It is true. Where do we write the true to represent the truth value of the whole thing? Answer, we write it under the ampersand. We write it under the main connective, and as the connective is just another word for logical symbol. And as there's only one, it must be the main one. So I write it true there, and to make it clear that this is the truth value of the whole thing, I'm going to circle it. Okay? That's how we do. All right. So, by analogy again with math, suppose I write 2 plus 3. How many numbers are there? 2. But, in effect, the whole thing is also a number. What number? 5. Yes, this is a way of writing something that is itself a number. Same deal here. We have two things with truth value, but the whole thing also has its own truth value. And the truth value of the whole thing is a function of the truth value of the component parts. That's why it's a truth function. We will learn how all the functions work in a second. What were you going to...
I was just going to ask if it, like, say you, is there like a logical letter that you would pick to represent every proposition? Or?
No. That's, if you use P's and Q's, it wouldn't matter. I just picked an O because orange juice begins with O, but there's no rules for that.
Okay.
Yeah. All right, let's do a bit more symbolizing. Next one would be Karen.
Either the Earth is flat or Barcelona is in Spain.
Symbolize that for me, please.
It's going to be F, little b, big B.
There you go. So F stands for?
The Earth is flat.
Yes. And B stands for Barcelona in Spain, which, incidentally, is a politically charged thing to say. Why? Because so what? Exactly, because Barcelona is actually in a region of Spain called Catalonia, and they were very much, actually, what happened recently in my country, the United Kingdom? The Scots had a vote on independence, which looked like it was going to be close, but ended up being not so close. And everyone in Barcelona was dressing in kilts and drinking Scotch whiskey, which they don't normally do. Because they approved of this separatist movement by the Scots because they want to do the same thing. The only difference is that the Spanish government says, hell no you don't, and then they're saying they can't hold an independence referendum, but they want to. But we're not going to get into that, and technically Barcelona is in Spain. So, then what is the truth value of B? True. What is the truth value of F? I'm glad to hear you say that. Believe it or not, there are some people who think that is true.
Weirdly enough, it's an international community.
It's an an international community. They probably think they can see each other if they squint hard enough. Yes, they have websites. They are called the Flat Earth Society. They really do exist. If you tried to reason with them, you would probably say, look at photos from space, at which point they would look at you pityingly and say, ah, you've bought into the conspiracy. All right, now we need a way of working out the truth value of the whole thing. What do you think it is?
True.
True. True. Well, somebody said true, somebody said false. We will find out shortly. Let's do a little bit more symbolizing. Josh.
If the Earth is flat, then all apples are orange.
Symbolize away.
F. Arrow. A.
Sure. What is the truth value of F again? False. What is the truth value of A again? And not again. False. Yes, confusingly, there is a British kind of apple called Cox's Orange Pippin, which is not orange. But there you go. It's delicious, though. Number 4. Ethan.
J, arrow, tilde, D.
Good. I am glad to see you following the rule and symbolizing the tilde. So what does D stand for?
That the Danube.
Danube.
Oh, Danube River runs through Africa.
That's right. So D says that the Danube River does run through Africa, and not D says that it doesn't. What's the truth value of J? True. In fact, did you know this? Jupiter is larger than all the other planets put together. It's that big. It's true. What is the truth value of D? Here I'm testing your general knowledge to its limits.
The Danube runs through Hungary, I think, right?
And is Hungary in Africa? No. So the truth value of D is?
False.
False. Yes. So that tells us that the truth value of not D is what? True. Now notice what I've done. I have written a false under D and a true under the tilde. Which of them is the truth value of the consequent of this? This one. Because the whole thing is not D. Now why don't I just write a T sort of halfway under the tilde and the D? You don't do that, because then you wouldn't reveal the truth value of D. I want to be able to symbolize that D is false. And then when the tilde is applied to it, I write the truth value of not D under that. So make sure when you write not D, you don't write them all squished up together like something like this. Keep your tildes as if they had their own space. Give them space. Make them large and proud. Otherwise it'll get confusing and cramped. All right, that'll do for symbolizing for now. We're going to do the whole sheet eventually, but we probably won't have time today. Now, we need to be able to work out how to work out the truth values of the whole things in these cases. We kind of knew it intuitively in this one. But what about this one? You say true? You're going on gut instinct and you don't really know. We need to have a hard and fast way of doing it. And the hard and fast way of working it out is something called a truth table. You will see many of these. You didn't see that. You didn't see that, see? You don't know nothing, see? Imagine if you will, you were given the task of explaining addition. You meet somebody your own age who speaks perfectly good whatever language you speak, most of you English, well, all of you English, but as a primary language. But this person didn't know what addition was, and you have to explain it. Now probably you do something like this. Right? You probably do something like that. Well, we want something a little bit more formal than that. And we want to be able to give them a way of working out what the sum of any two numbers is. Because, you know, even if they work out this one, 2 plus 2 equals 4, that's not going to help them with, you know, 300 plus 25. How could you do it? Well, here is an extraordinarily impractical way of doing it. But it would work, in theory. You say, okay, for any two numbers, you give them a table that has any of the two things that they're likely to want to add together. So, for example, if A is 1 and B is 1, then A plus B is 2. If A is 1 and B is 2, then A plus B is 3. If A is 2 and B is 1, then A plus B is 3, and so on. What would be the downside to this method?
Take forever.
It would take forever, literally forever, because there are an infinite number of numbers. So it wouldn't be very practical for numbers. But exactly the same method is very practical for truth functions, because instead of being an infinite number of values, how many truth values are there? 2. So you can actually produce a truth table that does that for, let's say, A and B. How many rows am I going to need? 4. Why am I going to need 4 rows? Because there's 4 combinations. They could both be true, they could both be false, or the first one could be true, the second one could be false, or first one false, second one true. Now, in fact, this ordering is what you're always going to use. Whenever you have a truth table with two propositions involved, you're going to do it like this. So think of it this way. The second column alternates, true, false, true, false. The first column goes 2 trues and 2 falses. So if you always do it like that, it'll make things a lot simpler. All right. Now, if we fill in the truth values for all 4 of these, that covers every possible use of and, because these are the only 4 possibilities in the universe. So you will then have a complete knowledge of how to use conjunction. Wouldn't that be special? All right, let's see if you already have a grasp of how to use conjunction. So, suppose I say 2 true things, like orange juice contains vitamin C and baseball is played with a round ball. What is the truth value of orange juice contains vitamin C and baseball is played with a round ball?
True.
True. And where do I write that true? Underneath the ampersand. Yes. What about orange juice is green and baseball is played underwater?
False.
So false and false. The whole thing is false. Okay, good so far. What about orange juice contains vitamin C and I'm an aardvark? False. So, all right, I'm an aardvark and orange juice contains vitamin C? False. Now the fact that these two are the same reveals what about conjunction? It has what feature? It is commutative. Yes, what does that mean and why does this show that? Because true false is the same as false true. Now I've already made this comparison before. Addition is commutative because 2 plus 3 equals, don't say 5, 3 plus 2. It does equal 5, good, but so does 3 plus 2. So addition is commutative because it doesn't matter what order you write it. So is conjunction. So A and B is logically equivalent to B and A. Yes, doesn't matter what order you write them. That is the truth table for conjunction. Now you know how to work out any conjunction if you know the truth value of both conjuncts. Okay? All right then. Notice, with conjunction, it's only ever true once out of the 4 possibilities. The rest of the time it's false. So it's actually hard for a conjunction to be true. What is the only time a conjunction is true? When both conjuncts are true. Any other time it's false. So notice what this means. What is the truth value of baseball is played underwater and there is intelligent life in the universe apart from us? How would you symbolize that? Baseball is played underwater and intelligent life elsewhere in the universe. What is the truth value of this one? False. What is the truth value of this one?
Doesn't matter.
If you know it, I will be suspicious that this is that we're in Men in Black, right? We don't know. Now that is not actually a truth value. I'm not saying that the truth value of that is question mark, because there aren't 3 truth values. There's only 2 truth values. All I'm saying is I don't know which it is. But I can still work out the truth value of the whole thing. What is the truth value of the whole thing?
False.
False. How do I know that if I only know one value?
Because you short circuit and you have a false in it.
Because anytime one of them is false, the whole thing is false. Okay? All right. That's logic for you. Now, I can be lazy because I'm working in chalk, but now you have to write out an entire other truth table. So get on it. Because we're about to do disjunction. All right. How about today is Monday or today is Wednesday? First one is true, the second one is false. What is the truth value of the whole thing, everybody? True. Almost everybody. Today is Monday or today, not and, we're now doing or. Today is Monday or today is Wednesday. The truth value of that is true. Right? That's how or works. What is the truth value of today is Wednesday or today is Monday? Also true. So what have we proved about disjunction? It's also commutative. A or B is the same as B or A. In fact, we knew that already because I told you when we did disjunction. You just forgot it with all the drinking you needed to do to get over the midterm. All right. What about I'm an aardvark or we're all dead? That is false. Right? So if both disjuncts are false, the whole thing is false. All right, now, remember when we were doing disjunctive propositions, vaguely you remember it through a haze, I said that there were 2 kinds of ors. What were the 2 kinds of ors? Inclusive and exclusive. Very good. Now I said that we're always going to use inclusive. But let's pretend we're doing exclusive. And actually the difference between inclusive and exclusive is just here. Both inclusive and exclusive agree on all of these. Where they disagree is here. With exclusive, what would be the truth value here?
False.
False. Why?
It has to be one or the other.
One or the other. They can't both be true. But because it's inclusive, the truth value is true. That is the truth table for or. Now, notice it actually agrees with and on the top row and the bottom row. When they're both true, both and or are true. When they're both false, both and or is false. Where it disagrees is in the middle. So where and was only true once, or is only false once. So what is the truth value of baseball is not played underwater, or there's intelligent life in the universe? The whole thing is true, because if B is false, what is not B? True. So we have true or something, and that is going to be That is going to be true. Why? Because there's only one way for an OR to be false, which is if they're both false. But as we know, that's not going to happen here. One of them is true. Then it's going to be one of these other threes, and in those cases, it's all true. Okay? Yeah? All right. Not necessarily exciting, but important stuff. All right. Draw another truth table. Well, I lazily just erase these. And we will, oh, incidentally, I haven't done the smallest truth table of them all. What would that be for? That would be for not. Why is that particularly small? Why is that not like that? Because it's unlike addition or multiplication, all of which, or subtraction or division, all of which have two inputs. It is like square root. Why is not like square root? It only has one input. So the one input we'll call A. So how many rows do I need? Two, because there's only two possible truth values that A could be. True, false. If A is true, what is not A?
False.
False. Where do I write that? Under the tilde, because actually under the A would be true, because we know what A is, it's true. But I write it under not, so what do I write? If A is false, not A is true. That one's so easy, I always forget to do it. All right, so that's the truth table for not. Let's do the truth table for conditional. This one's a little weird. And in fact, philosophers, believe it or not, still argue about this. We don't have to argue about it because there is general consensus that for most purposes this is fine. But it certainly has a couple of counterintuitive implications. Here is the way we're going to think about it, though. This is the way that, well, makes sense to me, and I hope it'll make sense to you. If-then statements are a lot like rules or laws. Like, if it goes up, then it comes down. You know, that might be a way of saying gravity, the law of gravity. Or if I flick the switch, then the lights will go out. That's a rule. Okay? It can be generally applied. So think of an if-then statement as like a rule. And here's the principle that applies. Assume that the rule is true unless it has been disproved. Okay. So here, the rule we're going to consider is, I jump off the weather ball, A is, I die. Which of these rows represents the real circumstances? 1, I have jumped off the weather ball and I'm dead. That is reality? I hope not. 4 is reality, because I haven't jumped off the weather ball, I promise you, and I'm not dead. Standing here, am I disproving this claim? If you jump off the weather ball, then you'll die. No, I'm not disproving it. So what does that mean? That means we say that it's true. Now that's a little counterintuitive. Because what is the truth value of, if Elvis is alive, then the moon is made of green cheese, according to this? True. Would you have said that if I came up to you and said, what is the truth value of, if Elvis is alive, then the moon is green cheese? Would you have said true? Probably not. But that's what we're going to say in this class. All right? Don't tell anyone or you'll get locked up. But if you think about it as, you know, if you jump off the weather ball, then you'll die, you don't disprove it. If you haven't either jumped off the weather ball or died, you haven't disproved it. So we assume that it's true. All right. Tragic. I do jump off the weather ball and I do die. Have I disproved the claim? Obviously not. If anything, I have confirmed it. I have gone to great lengths to confirm it. It's my dying action. I die a teacher. All right. Line 3. I don't jump off the weather ball. But tragically, I die anyway. I have a massive coronary and die in front of you. What would really happen is you'd say, great, class is over early, and you'd leave. But suppose that happens, okay? I don't jump off the weather ball, but I die. Have I disproved? If you jump off the weather ball, then you die. No, I have not. So it's true. What is the only way to disprove if you jump off the weather ball, then you die? To jump off the weather ball
And survive.
and not die. That's the only time a conditional is false. When the antecedent is true and the consequent is false. And if you think about it, this makes sense. Because what does the arrow mean? It means A is sufficient for B. But if A is sufficient for B, then A being true will guarantee that B is true. But if A is true and B doesn't happen, then clearly it's false to say that A is sufficient for B. Think about it. Makes sense. Now, what do these two lines show? Something that we already knew. It is not commutative. If you're a whale, then you're a mammal is true, but if you're a mammal, then you're a whale is false. Yes, so this is the first of them, whereas conjunction and disjunction are commutative, conditional is not commutative. Okay? Oh, but now we can prove something that I told you about before. Do you remember the Aerosmith Rule? I don't know if I called it that, but my example was somebody came on the radio and said, either you don't love Aerosmith or you want these tickets. What was the point of that example? I was trying to show that every conditional is equivalent to a disjunction. What conditional is either you don't love Aerosmith or you want these tickets equivalent to? If you love Aerosmith, then you want these tickets. Okay, so if you love Aerosmith, then you want these tickets is equivalent to either you don't love Aerosmith or you want these tickets. I said that these two are equivalent. How do I prove it? If the truth tables are identical. Because remember, way back in the beginning of class, I said two things mean the same if every time one is true, the other is true, and every time the first one is false, the second one is false. In other words, they have the same truth conditions. Well, these are the truth conditions. If they have exactly the same truth value on every single line of the truth table, then they're logically equivalent, they mean the same. Okay, how do we work it out? Well, A is true, so not A is false. Next one, everybody? A is true, so not A is false. A is false, true. A is false, true. B is true, false, true, false. So, false or true is true. False or false is false. True or true is true. True or false is true. Are they logically equivalent?
Yes.
Yeah, every time this is true, this is true. Every time this is false, this is false. Now, there's a quicker way to work this out. I know that this is a disjunction. There's only one way for a disjunction to be false, which is when? When they're both false. That's going to happen when B is false and when not A is false. When is not A false? When A is true. So this is going to happen when A is true and B is false. It's going to happen on this row, and the rest of the time it's going to be true. But that's the truth table. So, they're logically equivalent, and the truth table proves it. There's also other things that are logically equivalent to this, as you'll find out when you do your homework. Couple more things I want to cover. As I said, I've already said I'm going to postpone the homework, but please do look at it. What is the one logical symbol we haven't done yet? If and only if the biconditional. Yes. This one's easy. Think of it like an equal sign. If you think of it like an equal sign, what should I write under it? True. True, false, false, true. Exactly right. Why?
Those are the cases when the truth values equal each other.
Yes. when they're the same, it's true. When they're different, it's false. Now, that one's different from all the others because all the others are either 3 and 1 or 1 and 3. That's the only one where you have the same number of trues and falses. One more thing before I let you go. Here is a logical word, a word that has logical implications. The word unless. Let's work out what the truth table is for unless. Now, I did tell you the easy way to think of unless. I said it was equivalent to what two words? If not. So how would you symbolize A unless B? If not B, then A. Okay, so I can work out the truth table of unless if I work out this truth table. Alright, so A is true, true, false, false. Not B is false, true, false, true. In other words, it's the opposite of B. B is true, not B is false. False, so it goes false, true, false, true. Now, this is a conditional. How many times is a conditional false? Just once. What is the only time a conditional is false? When the antecedent is? See, this sunk in. When the antecedent is true and the consequent is false. What line is that? Number 4. So, this is the truth table for unless. True, 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 false. That should remind you of a truth table. What has exactly that truth table? Or. So what have we learned? We've learned that the word unless is logically equivalent to or. You're dead if you don't, no, what is it? You're dead unless you eat is equivalent to either you're dead or you eat. They're logically equivalent. Fascinating stuff, I'm sure we can agree. Alright, please check out your homework even though, well, currently it's still due Tuesday at 10, but I intend to change that and I will send out another announcement.